Welcome to the third lecture on Treewidth. Up until now, we have seen that how if a graph has separation number small, then we can exploit it algorithmically. And then, but if you try to do even max independent set, this algorithm runs in time n to the power big O of k time. So, in desire to design an FPT algorithm, we try to take an approach of dynamic programming. And if you notice, we give a dynamic programming algorithm for trees and also for the subclasses of grids. But if you notice for the trees, the way the problem worked was that for every vertex v, we rooted at some vertex root, and we had this notion of TV, which is basically a subtree rooted at a vertex v. And then we defined some subproblem, and in a bottom up fashion, we filled the solution to these subproblems and finally got our solution. Which was great. Now, an ideal way would have been an ideal approach or ideal way would be if a graph that has, so now let G be a graph that has vertex or separation number, say k. Now notice that the way we use this algorithm, the way we use this structure for computing max independent set while doing divide and conquer is as follows, right? So, how did we used? We actually found a separator S, and then we actually partitioned these two into two components where each of them had size at most 2n over 3. Okay. And now again we found, so basically in the beginning, we can think that we have this tree, because now what are you going to do? You are again going to find a separator for this component, something, and then you are again going to get smaller. So notice that this structure is like a tree. This is already giving us some sort of tree structure, right? So like there is an inbuilt tree structure when we decompose our graph, we remove, we have component, view, find. So basically, you can think of this that there is like, okay, or rather think, let's not think in terms of two, but like even if there have been several components, we delete some vertices and we have several components. So in some sense, what are we saying? Okay, fine, here's the tree. Okay, now let's associate this set S to this tree and say, hey, go and find a decomposition of these graphs or these components, say C1, C2, CL. So this is like component C1, C2, C3, CL. And suppose you are able to get some tree-like decomposition of these objects, right? So what happens? So like now, if I look at this root vertex, we say that, look, this is like, suppose I write G comma else. We say, look, this represents the whole graph, where if you delete this set S, you get into several connected components. So now maybe, right? So now for these guys, for these components C1, C2, CL, suppose inductively or in some way we are able to find some tree. Then in some sense we are able to get a decomposition tree for the whole graph by adding an extra node here and adding these edges to get a tree T. Okay. Now Now, these components again will have like whatever the component and some other vertex set is prime, and such kind of these things can happen. So notice that inherently when we are trying to do this divide and conquer and we are distributing the components, the way these components are forming actually is a tree-like manner or a tree-like fashion. Okay. So that tells us that if the graph has a small separators everywhere, right, then we should be able to exploit this structure to also arrange this graph in a tree-like fashion, and we say, look, this part of the graph is associated to this kind of tree, and so on and so forth. So this is the kind of objects we would like to say. So what are we saying? That given a graph G, our goal is to associate a tree T, okay, in a way that pieces of, so and what else do we want? Pieces of graph separated by some s is represented well. Okay. Okay, is represented well. Okay. So in some sense, what are we going to do the way we had for the tree? So what are we going to do? So like if you recall tree, we had this tree and we automatically had an association. Look at V, what was TV? TV was subtree rooted at V. Now our graph is not a tree, but I have a graph G and I have a tree T. Okay. So given a graph G, I would like to associate a tree T, and now what I would like to say, I would like to associate, look at a vertex set of T, right, and you are going to associate not one tree, but not one vertex, but associate a vertex subset of Vg. Okay. So this is what the function will do. Now, okay, so and you will see what this generally. So we'll get to that how we do these things. But now, what will this mean? What kind of graph? So suppose this is a T, and I have a vertex V. Okay. Now TV will again mean this, but what graph do I consider? But now this will be graph induced on union, okay, T. So like with respect to TV, the graph associated will be graph induced on T in vertex set of TB and f of t, meaning look at the vertex sets, look at this function f, it is assigning some subset of vertex here, 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 here. Basically, you take the union of all these vertices involved in these sets, okay, that is a graph it represents, okay. And so association of a node T in Vt to a subset of Vg is called a bag. Okay, so we'll call a bag. Okay, because look, so basically it tells, look at this tree, every vertex in tree is associated with a subset of my graph, a vertex subset. Now look at this tree, root it at somewhere, and look at any vertex, you have a notion of subtree rooted. Now I ask myself, okay, when this itself was a tree, then the meaning was that this is a subtree rooted at T, is this part of the set. But what part of the graph am I considering? This is basically the graph which is union of graph induced on union of vertices which are appearing in the bags which are associated below this vertex V in the tree, right? So there is a natural association of what graph to consider. Now you may ask, what are these bags? So basically, as I was trying to tell earlier, look, when we are separating, right, this S, so this association, this function will basically try to take a piece of the graph and associate that set S to this vertex V, right? So I say, look, now I'm going to make a tree where I'm going to make an association. Oh, I'm going to separate S from here. Let's make a node V in the tree, and we will make all these things clear. I'm just trying to give a motivation how people might think about how to get a decompositions. Okay. So this is the kind of things people try to do to associate. And now let's get to, so what is the natural way of going? Okay. So for the MIS, what did we do? We said, okay, fine. Look at a set X, okay, and look at a connected component, several of them, say C1, C2, dot, 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 CL. Okay. What did we do when we were doing divide and conquer? We actually branched on X and concentrated on graph induced on C1, so the graph induced. But if you notice, there are also edges here, right? So when we are trying to decompose our graph, it is important that the piece of the graph we are trying to decompose is also there, because look, like one particular strategy worked for designing an algorithm from max independent set. But now, given a graph, we would like to decompose such that there is an information about every vertex and edge in the graph in my decomposition itself, right? So rather than when we get an X, we say, look, rather than say, okay, find a decomposition for C1, C2, this, the way we will try to work is that so that every edge is counted in somewhere, because look, for example, if you would have been doing, say, max cut example, just to understand that why it is important that you don't just focus on graph induced on C1 to CL, but actually we should focus on graph induced on C1 union X, graph induced on CL union X, when we are trying to recursively decompose my graph into smaller pieces. Why? Because X acts as a porter or as a barrier when going from any component to any component. And say, for example, suppose I will tell you suppose I was trying to solve a problem such as max cut. What is this? Input is G, output V1 disjoint union V2 of V of G, that is partition of Vg, right, such that number of crossing edges are maximized. This is what is the classical max cut problem is. Now, if you find a set X here, right, what will be the natural way of branching? We will, okay, look at an optimal partition. An optimal partition could be in one part could be this, other part could be this. So this is basically going from x1, x2, x1 prime, x2 prime, basically 2 to the power mod x ways of partitioning. Okay. Now, given this partition, notice, look at a component here. Suppose I had a component here. Okay. Now, it is important for us that how these edges are there. Look, and if I forget this red edges and find an optimal partition of this, that may not lead to an optimal partition. I cannot combine a solution to this, to a solution here. It's because this red edges are across the cut or not also depends on because these red edges also needs to be counted in the cut, and hence it is important for us that rather than recursively trying to solve just on the component, we actually solve the problem on graph induced on C1 union X. Okay. So because of all these things, it is important that whenever we are doing a graph decomposition, we make the graph decomposition as natural, as general as possible, so that you can exploit the decomposition of a graph to make or to solve or design algorithm for as many problems as possible and not only max independent set. So a natural way people go about doing is that whenever we are decomposing, it's exactly the same way the divide and conquer tells us, okay, fine, in a tree-like fashion you do it, but now what happens? So basically what we are trying to do is that we get this set X, and then here are some components, okay. Now what are we going to do? We say, okay, fine, okay, let's decompose this piece of graph. This is one piece of graph where the common. Let's decompose this piece of graph. Let's decompose this piece of graph. Okay. So, and what is their common place is the set X, right? So, once we have been able to decompose these pieces, we will put them together. But here is something like a natural question is whenever we are decomposition, right? And whenever we are trying to make this tree, okay, I told you that we should write the object which helps us in decomposition. So, so whenever I'm making tree for this particular node, I will say, okay, X is a set which separates the current graph. Okay. But notice that what is my objective? So whenever I was doing DP or something, right, it is important that the set of vertices who has neighbor outside, right, who has neighbor outside, okay, is part of my separator. So in general, what we try to do is that at any point of time when we are trying to have, so we have a graph, okay, and we have a separator here, okay, and these are the only vertices which has neighbors outside, okay, like, I mean, rather, suppose this is X, okay, every vertex, say this is some VW, every vertex in VW that has neighbor outside X is also part of neighbor outside VW is part. So if a vertex is here which has a neighbor to some other vertex, then this guy must belong to the set X. Okay, so this is the property of this. Now notice that recursively when we have this piece of the graph, we'll try to find. Okay, now let's further split it. Now if we further split it, it is possible that we find a decomposition this. So now notice that a vertex which was previously used for cutting now can also be used for cutting further. And what does it imply? That if a vertex at any stage, if a vertex has a neighbor outside, it remains so even when we go recursively below. So now because of that, if you notice, if I have a tree, right, what it tells us? This is basically tells us when I look at this set, oh, look at the graph below. Okay, these are the vertices which has neighbors outside. Now notice it means that wherever these vertices, now if I look at the graph here, right, and if this vertex V also is here, it means this guy also has neighbors outside. So if all I am storing at any point of time, suppose look at this decomposition, what I am storing at any node V of this tree, I say look at the graph V and for any graph V, I am containing a set, say here xv, and what is the property of xv? The property that any vertex here, if it has an edge outside, it is a part of xv. Now notice that it implies, look here, as I told you, right, a same vertex could appear several times in helping us in separating. So every time it appears in separating, it could, and hence and as well as when once it becomes a part of boundary, it becomes boundary. It means what happens? If V appears here, V appears like, look at some vertex, look at this set I think I have used, I think I should not use the vertex. I think we should use some z here, okay, xg. Okay. Now, the point which I'm trying to tell you is that it's very natural because of all this that if some vertex, look at, so what are we associating to? So what I want to say is that look at what we are associating to a tree, some subset of vertex. Okay. So suppose this is V1, V2, V3, V4, and suppose here we have associated XV1, XV2, XV3, XV4, and suppose some vertex Y of Vg appears here, okay, and now suppose Y appears here, then my claim to you is that Y must also appear in XV2. Why? As I told you. So at any point of time, okay, the set of vertices, basically what are we storing here is the set of vertices from below who has a neighbor outside. Okay, already has. So if this Y already has a neighbor outside, okay, so like it's going to contain all these vertices. Now look at XV2. If Y is here, it means Y also belongs to the graph induced on this. It means Y also has neighbor outside, which implies Y should also belongs to this. In some sense, this is exactly what it's trying to do. So basically what I'm trying to tell you that we need some property from these bags, where what is the property that if some vertex appears in several bags, okay, then look at the set of vertices that forms of the tree whose corresponding bags this particular vertex appears, then they should be connected. They shouldn't be disconnected, because keep in mind, I'm just giving an intuitive picture. So what are we trying to store? At any point of time, I have a piece of graph, and the set which I'm storing at this particular vertex is those vertices in this set which has their neighbors outside. Okay, so if a vertex had a neighbor outside before, it will remain so if this vertex appears in any smaller induced subgraph, so on and so forth. So there are a few specific properties that we need to maintain, and to do all these things, people came up with this notion of tree width, which I'm going to define now. So up until now, it was just like, at least whatever I try to give you is the set of properties that that we should expect from the tree decomposition or the tree width or the decomposition which we are going to define now. Okay. So let me not waste my time and formally define these three things. And once I have formally defined these things, try to go back to the 2-3 properties that I have been talking about up until now and see where do they fit in. Okay. So let me formally define this. So what is the tree decomposition of a graph G? So tree decomposition of a graph G, okay, a tree decomposition of a graph G is a pair. What is a pair? Okay, is a pair T equal to an xt, okay, T in Vt. Okay, and what is this property? What is this? Here, T is a tree for every node T of vertex set of T, a vertex subset xt of vertex set of G is assigned. Okay. So basically, the way I have been explaining up until now, so basically a tree decomposition graph is a pair, a tree, and xt, which is like for every node you are defining what do you call, associating a subset of vertex set. And what are the properties? That is like it satisfies some very basic property. Okay, pair tree that satisfies the following properties. Okay, so what are the basic properties? So the property first is tree decomposition property is that if you look at union T in Vt and you look at xt, this is equal to vertex set of G. Like every vertex appears in some bag, and it makes sense, right? I mean, okay. T2, okay, is that for every edge uv in E of G, there exists a node T in vertex T such that u comma v is a subset of xt. Meaning for every edge uv, there is some bag that contains both u and v. Okay. This is also like, you know, like every edge occurs somewhere. And finally, and this is an important property that we have been talking up until now. Okay. And what is T3? For every u in Vg, okay, for every u in Vg, the set Tu, okay, what is the set Tu? It is those nodes in vertex set of T such that u belongs to the corresponding bag, okay, that is nodes of T whose corresponding bag contains u. Okay. So, for every node the set Tu, okay, induces a connected subtree of T. So, what is the meaning of this? So, basically, so what it basically says is that we will come to that. So, we have a graph G. Okay. For a graph G, I am going to associate a tree and some xt. Okay. So, basically think of this xt, I mean, which I use the function f before, and that, or people actually use the function beta to represent this, but like basically I have a graph. For this graph, I have associated a tree, okay, and for every t in Vt, okay, I have associated some xt, which is a subset of vertex set of G. And what is the property? For if you give me a vertex V, there is V is going to appear in some xt of some node here. If I am going to give an edge uv, it is going to occur in some bag. But the last property tells us, look at a fixed vertex u. Now let's look at all those nodes which corresponding. Let's look at u in Vg. Now let's look at all those bags that contains u. So suppose it contains this, u is part of this, u is part of this. Okay. Now look at the tree induced on red color vertices that must be connected. So for example, the picture which I have drawn here is not right, because look at the tree induced on these 3 red vertices, it is disconnected. So basically it means that even this vertex must be included, right? And as I told you, right, we will see a proof, but basically it's like we are trying to decompose via separators some pieces of graph, and once you become special and define special, if you appear in some separator at some point of time, then you remain a special, because I mean, why are you a separator? Because the reason you are a separator, and I mean, right, so we will be only dealing with some minimal separators. It means because you are separating someone from somewhere, it means this particular vertex must have some neighbor outside. And so basically every vertex that appears in separator is kind of external for that piece of the graph. And once you are external for that piece of the graph, you remain external for every piece or the connected set in which you are part of below, right? And hence you are part of that band, which implies that once you are not, like you are gone. So this is important to maintain this property, and you will see that how this connectivity property of this subtree is an important way exploited algorithmically. Okay, so that was to give you some basic. Now, so this is the definition of tree decomposition of a graph. So tree decomposition of a graph is a pair t comma xt which satisfies some property. Okay, and what is the width of a tree decomposition? Width of a tree decomposition, okay, is equal to max over t in Vt. Okay. So basically width of a decomposition is maximum bag size minus 1. And the reason why there is a minus 1 here to classically mean that, okay, tree should have tree width 1. Okay. Now you may ask, so what is a tree decomposition of a graph? Okay. So tree decomposition of a graph G, okay, is basically decomposition, okay, is a decomposition basically, okay, let's say, is a tree decomposition of minimum width of G, right. So for example, right, tree decomposition is a minimum width of G. Okay, right. So given a graph G, I could have several decomposition of that graph. Okay, but tree width is find the decomposition where the width is the smallest, where no bag is larger. So whenever I say tree width of G is at most k, implies there exists t comma xt such that for all v in Vt, size of xt is upper bounded by k plus 1. Okay. So basically I can find a tree decomposition of my graph where no bag has size more than k plus 1. Okay. So having said all this, let's try to make our hands dirty before we can, and we will also prove some structural properties later on, is that let's try to construct some tree decomposition. Okay. Let's make a mark. Okay. Constructing tree decomposition. Okay. Okay. So for any graph G, here is my tree decomposition. Okay. So graph G, you have single vertex V. Okay. So my tree consists of single vertex, and you suppose this is V, xv equal to vertex set of G. Definitely it satisfies all the property, every vertex appears, for every edge there is a bag containing this, and definitely for any vertex it appears only here, so it's a connected thing. Okay. But this is like a most trivial decomposition. Okay. And so for any graph G, what does this imply? The tree width of G is at most n minus 1 if vertex set of G is size n, right? Because you have added everything. So, okay, so we do know how to compute a tree decomposition of a graph. Now, let me take a suppose this is my graph triangle. Okay. I can make so if I make a trivial decomposition, this is a trivial decomposition, that implies that the tree width of a triangle is at most 2. Question: can we make one with tree width at most 1? And notice that because we need a bag which contains an edge, which implies that the tree width of triangle is at least 1, right? Because you need to have a bag containing at least 2 vertex. So any graph which has an edge, the tree bag must contain 2 vertex. In particular, a bag containing the endpoint of a particular edge. Okay, which implies that the tree width of a graph which has at least one edge is at least 1. Okay, so I know the tree width of a triangle is at least 1, at most 2. Is it 1? It's a good question. Please try. Okay. Okay. What about path? Okay. Remember the way we made our DP algorithm? Okay. So this is our path. Okay, and suppose path as a T, I am going to take P itself, and suppose this is V1, V2, V3 and Vn. So I am going to add xv1 as V1, and so think of this V1 rooted at V1. Like, so what is xv1 going to contain? Xvj, let's say. Xvj is going to contain Vj and its parent, right? So this is going to be Vj plus 1. Okay. Now let's see if this satisfies all the property. Well, yes, right? Every vertex appears in someone. Okay. And now look at about edge. Look at any edge Vi plus 1. That edge is part of the set Xvi. Okay. Now look at a vertex V. It is a part of which one? So look at a vertex V. This is going to be part of a bag which is here, and it is going to be a part of the bag which is there. But if I look at so these are the bags in which this particular vertex appears, but that is an edge. So this is connected. So this is a valid tree decomposition. And what is the width of this tree decomposition? Tree width of path is at most 1, because every bag has size at most 2. Okay, that's great. Okay, now let's prove another nice result. Okay, small lemma. Let G be a graph. Okay, and X be subset of Vg. Then tree width of G is less than equal to tree width of G minus X plus cardinality of X. Let's prove. This is easy. Okay, so here is my X and here is my G minus X. Okay. Now for this G minus X, suppose we have tree T and some xt for G minus X. Now what will we do? Okay, what will we do? Say for all t in Vt, let xt equal to xt union X. Okay. Now that's it. Now let's see why all the 3 properties are satisfied. Look at every vertex. Definitely already every vertex of G minus X appeared in the xt, and every vertex in X appears everywhere. So this is perfect. Now look at an edge. So there are kinds of edges. Where are the edges? Edges are either here, here or here. These kind of edges are anyway taken care because this is a tree decomposition of G minus X. What about edges which are going across? But now look at somewhere this vertex V appears in xt, but in that you have also added the whole of x. So V and that x is also taken care of, and since x is in every bag, all the edges from here is also being taken care of. Now look at the connectivity property of a vertex. Look at a vertex in G minus X, that is like all the bags in which it occurs, it's already connected because t comma xt is a tree decomposition of G minus X. Now look at a vertex x in X, but that X occurs in every node. So that is, since T is a tree, it is already connected. So this is who just tells us that if you have a tree graph G and you have a set X, then if G minus X has a small tree decomposition, then G minus X and then the G itself could have a small tree decomposition. Okay. So now let's exploit this lemma. What about the tree decomposition of cycles? What about tree decomposition of cycles? Okay, fine. For triangle, we could give is at most 2. Okay, but now let's see what we can do. Okay. Suppose delete W from C. What we are going to get? Then this is a path P, for which, and here's a W, right? Right. For path P, we know how to compute a tree decomposition, right? Compute tree decomposition of P of width at most 1, which implies by adding W to every bag, we get tree decomposition of C of width at most 2, because we just applied the previous lemma, right? Now path has tree decomposition of width 1, then you add whatever. So this is how we could add. Okay, let's do further. What about tree decomposition of wheels? What is wheels? It's a cycle and there's a spoke, right? Okay. What did we prove? Tree decomposition of cycles has width at most 2, and suppose this is a W, delete W, what are you going to get? Cycle. So tree width of wheels is at most 3, because 2 here and you added 1 from here, right? So look at this, how interesting this lemma is. Okay. Now let's do more things, and let's say now let's do trees. Okay. Trees are no different than paths, but we'll see. Okay. So suppose this is my tree. Okay, suppose this is my tree. Okay, so I just root at some vertex root. Okay, so my T is going to be same. Okay, and for any vertex V, xv is going to be V, and again parent of V. That's it. We are done. Okay. Now, by definition, every vertex appears in some of the bag. Look at any edge. So for any edge, one is child, one is parent. So look at the bag of the child. In that you have this. So this is perfectly fine. No problem at all. Now what about a vertex V? So look at a vertex V. Where all a vertex V appears? A vertex V is going to appear in all the bag of its children and itself. Okay. Every V appears in the bag of itself and children. Okay. every V appears in the bag of itself and children. What does that imply? This implies that bags that contain V form a connected subtree. Right? So, yeah, okay. Now, so what about grids? Okay. Okay. So now we have done. So okay. So now what about this is my lemma. Let H be a subgraph of G, then tree width of H is less than or equal to tree width of G. Okay. This is very simple, right? You take the tree decomposition of G and okay. So a tree decomposition of G is also a tree decomposition of H, and you are done, right? Because every vertex appears already in G, every edge appears already in G. If a vertex is connected, then the vertex is connected still. So, this is perfectly fine. So, this is great. So, tree width is a property which is closed under taking subgraph. Okay. 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 So, now what about another lemma? Let us try to prove. Let UB be an edge of G, okay, and let G contracted UB be the graph obtained from G by contracting UV. What is contraction means? If you recall correctly, so basically what is the contraction? This is an edge. So basically you make a new vertex UV, okay, and make this guy adjacent to all the edges which were adjacent to UV. So you basically delete U and V, add new vertex UV and make it adjacent to every vertex either U or V was adjacent to. Okay. So, what are we saying? We are going to say that the tree width of, so this is another operation which does not increase the tree width, and this is proof is very simple. Okay. Now, what is tree width of G? So, tree width of G is like, so tree, because, so look at the tree decomposition of G. Decomposition of G. Okay. And if some t, if xt contains either u or v, replace it with uv. So, yeah, so if you like, it might just contain u or it might just contain v, then you still add uv. If it contains both uv, you delete both uv and just replace it with uv. So, notice you have not increased the bag size. What about edge property? Well, I mean edge property is anyway satisfied because, right. And now what about uv? Look, what about the connectivity property? So, look at the connectivity of u and v, right. Look at u. So, u is going to be some subtree which is connected, and look at the v, right, that is going to be some subtree which is connected, right. But the blue subtree and red subtree must intersect, because why they must intersect? Because look, uv was an edge. If uv is an edge, there is a bag that contains both u and v. It means, look at, it means there is a bag which is common in the red bag and the blue bag. So, now if the two connected things intersect, they are connected in itself. So, which implies that the bags of uv also forms a connected subtree. Okay, so this is okay. Okay, so here's my exercise. Okay, okay. So let me define a graph H is called minor of G if H can be obtained from a subgraph G prime of G by contracting edges. Okay. So, what is this tells us? I am going to call H is a minor of G. Okay. If you can get H as follows. So, from G first you get a subgraph G. So, basically you delete some edges. So, G is delete some edges. So, this is one. And now you should be able to get by contracting some edges of G prime. Then I am going to call H is a minor. So, a graph H is called a minor of G if H can be obtained by following operation. You first take a subgraph of G and then you contract some set of edges. Here is an exercise for you. You should be able to prove. If H is a minor of G, then show that Treewidth of H is at most Treewidth of G. Okay. 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 So, the last example which I want to make or construct is grids. Okay. So, suppose I have this k times n grids and I have column 1, column 2 and column n. Okay. So, actually I am going to give you a path, I am going to give you a path, not even tree. So, what is my path? Is basically consist of a path on n vertices. Okay, V1. Okay, so let's, since we are using T1, T2, Tn. Okay, and what is XTI is going to be column I union column I plus 1. Okay, this is it. So, T1 is going to consist of what? It is going to basically consist of this set and this set. And what I am going to associate to T2? I am going to associate to T2 column 2 and this. What I am going to associate to column 3, like the T3 is basically so on and so forth. Now, definitely and you might ask what about XTN? So, for XTN I should write XTN is nothing but just column n. Now, notice every vertex by definitely every vertex appears in some. Now, look at any edge. If it is an edge which appears in a column, some particular column itself, then that occurs, or any other edge is between some column I and column I plus 1. And I know that Ci and Ci plus 1 are together in Ci. Okay. So, that is done. And what about, look at a vertex appears in only two bags. A bag, like a bag which consists of either, so suppose if a vertex appears in column Ci, then this vertex is going to appear in the column like the node corresponding to Ti minus 1 and Ti itself, right. So, like basically every vertex appears on two consecutive nodes on my path, and hence their bags, hence they constitute a connect. So, this is done. So, what are we able to show? Okay. So, we are able to show if we have k times n grid, then Treewidth of k times n grid, okay, let us denote grid by grid, is at most 2k minus 1, because 2k 1, right. So, this we are able to show. Okay. So, here is my question exercise. Let us say show that tree width of k cross n grid is at most k, right. It means you need to come up with, tree decomposition where each bag had size at most k plus 1. Okay. Try this, it is a simple and easy exercise. Okay. And before I end my today's lecture, let me make a last comment. Okay. My last comment is that we assume that we have a k cross n grid, but actually suppose we had some k cross l grid. We could also make another tree decomposition where we take these two together, then this two together, and these rows together. So, that will imply that the tree width of k cross L grid is actually minimum of 2k minus 1 2L minus 1. Okay. And here is another exercise. So that tree width of k cross L grid is actually minimum of k comma L. Okay. And yeah, so we will have another lecture later for this week where we will show some structural properties of this tree decomposition. So, up until now we have seen how to construct what this tree decomposition, and I have given you some fairly several examples of construction of tree decomposition, and I will show you how people use this tree decomposition in parameterized algorithms in the next lecture, as well as give you some structural properties of this tree decomposition, and that should be all for now.